Welcome to this, the first in our series of optimization talks. There'll be a total of 4 in total. And in the first one, we're going to define the scope that we will be considering. Optimization, there's actually an awful lot you could say about it, and then you could delve into this in an awful lot of detail. We'll mostly be concerned with looking at the coding side and some optimizations that certainly are applicable to C++, but are more broadly applicable across programming languages. The notion of optimization, it ties in very closely with the notion of efficiency. That if you are trying to optimize your program, you're trying to improve its efficiency in a certain area. And it's key that we're talking about efficiency in a defined area. Most typically, it tends to be CPU cycles or memory usage. That you can have a program that, if it's efficient in terms of its use of CPU cycles, it means it's not using unnecessary cycles. If it's efficient in terms of its use of memory, it's not storing more data than it needs to. Important to note here that you can have a program that can be optimally efficient. That does not necessarily mean that it's going to be fast or use very little memory. So for each problem, there will be fundamentally a lower bound, a minimum amount of computation or minimum amount of storage that will be needed. And for some problems, that is a fairly large minimum bound. So by efficiency, by optimization, we're trying to say, let's just get it running as fast as it possibly can or using as little memory as it possibly can. Important to remember when we're talking about efficiency here, we're generally focusing on one area. Normally doesn't work out to say you want to have something that is optimally efficient in terms of CPU cycles and memory usage. You pick one, and quite often some of the efficiencies you can put in or the techniques trade off the other to provide you with a gain. So efficiency, there's 2 main areas whereby we can try to ensure we have something that is efficient or to improve our efficiency. One's through the design, and then the other's through how we actually code it. So the design, that's language independent, may bring in some architectural aspects, but it's our model of the thing that we are trying to implement. And it generally has the biggest impact on efficiency. So if you get the right design, you're well on your way to having an efficient implementation or an efficient program. For the coding efficiency then, this is how we take our particular design and turn it into runnable machine instructions on whatever platform that we're using. For design efficiency, we can subdivide this somewhat. Ties into 2 broad areas. One's the algorithms and data structures that we are using. So the types of sorting algorithm, searching algorithm, access algorithms that we use, the types of data structures that we use alongside those. For the program structure, this looks at how we have decomposed the process into different objects, different classes, how they're linked together, and how we are viewing the if you like, the flow of control. How many subtasks do we think are involved within this? How are we calling those subtasks? How are we sequencing them? So at this level, these are the main factors that we get to play about with. And just to reiterate, these are the things that count. That if you do this wrong, you will potentially have something that is very inefficient, and there's nothing you can do about it in terms of the coding side. So it's important to get this right first of all. For coding efficiency, there's sort of 4 areas here that we've subdivided it into. One is in terms of the language construct. So different languages will provide different features, and we want to use the features, the data types, the language constructs that are available to us that enable us to implement this in an efficient manner. Architecture then is the next thing, in the sense that we are producing machine instructions that will be running on a particular device, and that device will have certain characteristics. So it may have a certain amount of processor cache that we can store data within. You may have a CPU and a GPU, and there may be some functions we can run in the GPU and run them in an accelerated manner. Libraries, generally, these programming languages we're looking at, they'll have a bunch of available libraries. Some of the implementations of the libraries will be wonderfully fast, sometimes maybe less so, but we can pick the appropriate libraries and library functions that will be efficient for whatever we have in mind. Then we get into compiler optimizations about how the compiler tries to take what we have written and turn it into something that is executable, but efficiently so. So a lot of optimizations there for things like loop unrolling, for constant expression evaluation, some of the stuff we looked at earlier on. Compiler may do this, equally the programmer could introduce it him or herself. Now, the design choices we make, as we have mentioned, they're going to have the greatest impact on efficiency, and we should always be striving to produce a design that is efficient, irrespective of whether or not efficiency is an important thing for us. We want a good quality design that is, at essence, efficient. That's always important. Sometimes, however, and you would be benchmarking, you would have some performance targets. If you don't meet that, if you want to have a truly efficient program, then you generally have to marry your efficient design with efficient coding to have both of these together. Takeaways on this, as Randy mentioned, the design decisions, that's going to have the biggest impact on efficiency, probably. These are things we should always be concerned about. But sometimes, if you're not meeting your targets, or if you're doing a library where you want this to be broadly shareable, you have to then get on to looking at how do we code it, the efficient design, how do we produce efficient code for that particular design.